OS is an operating system, and when we apply apply an update to the server, we need to reboot the server to get the new kernel and stuff like that. So as we were building out this operating system and realizing, oh, hey, we need to be able to reboot the server, we discovered that when you're thinking about a cluster and you have lots of servers that might reboot at once, you need some way to coordinate that. And this was sort of the initial drive for building something like etcd to provide that cluster-level coordination. And then also, in terms of, as I said, in terms of thinking of it as etcd distributed, you need some place where you can share configuration among all your machines in the cluster. So there was an existing, the main existing sort of solution in this space was, at the time, was Zookeeper. But we, some of us had had a lot of experience with Zookeeper and not had a very good experience. And we also found it very sort of inflexible. As far as we're trying to build really simple tools that have simple integration points. And the Zookeeper API was, for a long time, was kind of undocumented, sort of implemented in sort of one library that a lot of people would link against, but took a long time for, actually I think some of the Python developers spent a long time sort of unwinding and reverse engineering the API in order to document it, but at the time it was a nightmare. And it was also, Zookeeper was very inflexible in terms of reconfiguring, so if you want to change membership in the cluster and stuff like that. So that was kind of a key drive to create etcd. So why should you use etcd? Sort of a quick pitch is that, well, it's great. It's highly available, it's extremely reliable. So we can extensive testing and lots of production cases. It provides these strong consistency guarantees that you need when you're building higher order distributed systems. It's very simple to use. It's a very simple API, and it's quite efficient, and it's all open source. All etcd development happens open source on GitHub, and we have sort of regular community meetings as well. And that's sort of the way we're trying to pitch etcd, or trying to describe etcd now, is that it's like for the most critical data of the distributed system. So we have had some interesting use cases, where people will try to build a whole file system or use etcd as sort of a pub sum or things like that. But it's really, it's not tailored towards those use cases so much. It's really focused on stuff that absolutely has to be safe in the system. So as an example, like if you were to build like a distributed file system, we wouldn't want you to store the file contents in etcd, but maybe it would make sense to store just like the file metadata in etcd or something like that. How does etcd work? As I've sort of touched on a couple of times, etcd is based around this consensus algorithm called RAF, which is started by a student at Stanford, PhD student at Stanford a couple of years ago. Really interesting algorithm, interesting paper, which I highly recommend everyone read. And there's also a great website which we'll just sort of go through it briefly today. It's oriented around these three key concepts of like elections, leaders, and terms. And so the idea is that etcd, a cluster of etcd machines will elect one leader for a particular period of time, and then during that term, that leader is responsible for all the changes to the state machine. So you only ever have one machine at a time in the cluster actually sort of doing the changes. But then RAF provides sort of these safety guarantees around that, and it also provides a process for if that leader happens to die, how do you find a new leader? And then, yeah, etcd is fundamentally it's a Go program. It's 100% pure Go implementation, and then it consists sort of the main two components to it are the etcd binary, which is just a single daemon that hosts the etcd API for clients, which is, as I said, it's an HTTP API. I'll show you what that looks like in a second. And then in terms of when the etcd nodes are communicating amongst each other, they're using protobuf of HTTP. And then we have a simple command line client called etcdctl, which allows you to play with etcd. We use a ton of, pretty much all the standard kind of Go standard library things, lots of HTTP, encode, JSON, this kind of thing, and the Go protobuf bindings. So just talking a little bit about etcd, like what it looks like in a cluster. The basic idea is that you would always have a cluster of, well, typically you would have a cluster of 3 or 5 machines. Sort of the reasoning behind that is that obviously the more machines you have, the more resilient it is to individual machine failures. but in terms of, since you're trying to get consensus among all these nodes, then that's going to increase the latency to get all the machines to agree on something. So 3 or 5 tends to be a sweet spot. There's plenty of there's various sort of analyses out there of why that's the case. But yeah, again, the idea is to be resilient in the event of machine failure or in the event of machine reboot. So even if you lose a couple of machines from your etcd cluster, or they go available for some reason, etcd is still available. You can still write to it, you can still read from it, and as long as you maintain a simple quorum of the machine. So in this case, 3. As soon as as soon as you lose quorum, then etcd becomes unavailable for writes and only unavailable for stale reads. Just talking a bit about the current API. As I said, it's very simple. Suppose it's mostly the kind of get set operation, and this is just expressing it in terms of HTTP verbs. So you can literally just get the key foo from the key space. The interesting thing with get is you can do waits. So when I was talking about pub/sub earlier, this is sort of how people might implement pub/sub using etcd. So using HTTP long polling, you can, as a client, you can register sort of your interest on a particular key. Anytime that there's a change to that key, you get a response back from etcd saying what happened to that key. Then you can replace the existing value of the key or delete the key. That's all pretty basic, but when things get more interesting and when what actually makes etcd interesting for building distributed systems is these two atomic operations that it exposes. The first of these is compare and swap. So the idea here is that you can optionally set the value of the key if the current value is something that you precondition that you give it. So in this case, we're trying to put the new value to the key foo, but we're only going to do that if the current value is equal to bar. So if that's the case, then the set will happen. Otherwise, the operation will just fail, and etcd will just return an error code. We communicate mostly through through some sort of structured error code saying that the value didn't match, the precondition didn't match. Similarly with compare and delete, except in this case, the operation is just to delete the key. So these primitives allow you to build things like locks, because you can have clients can safely know that the only person, or that they were, for example, the last client to mutate a particular key because they set it to the known value. And then, the easiest way to use the API from Go is that we have sort of an upstream etcd client package, which is pretty straightforward, pretty robust, and it handles a lot of the stuff around like discovering the etcd cluster and updating the list of members in the etcd cluster as the member configuration changes and things like that. So if you want to play with etcd from Go, I encourage you to just use the native client. So I want to talk a bit about some of the applications that use etcd. One of sort of the classics examples, which is again sort of one of the main motivations for us in developing etcd, is something called Locksmith, which is in the CoreOS Linux distribution. So as I said, CoreOS, we're trying to update machines pretty regularly and automatically, so we don't want there to be any user intervention. So when an update gets applied, then the machine goes down for a reboot. And obviously, you don't want your whole cluster rebooting at once if they all get the update at once. So we need some way to safely reboot machines sort of individually without any user intervention. And the way we do that is by implementing essentially a semaphore primitive in etcd, and then having all the machines in the cluster talk to etcd and interact using that semaphore. So for example, if we had a cluster, here it's a pretty simple cluster, just 3 machines, and then at the top, at the etcd node there is you think about it as the etcd cluster, 3 acquired machines. And then at server 3, it's just received, it's just downloaded and applied a new update, and it needs to reboot to get that update. So in CoreOS, we use an active passive partition scheme, so the update will always you'll always be running in the active partition, and the update gets written as sort of as a whole block device to the passive partition. Then we reboot into the passive partition to apply the update, because the root file system is always redone. So when that machine needs to reboot, what it needs to do is needs to talk to etcd and access the semaphore, and then using the compare and swap that I just talked about, it can atomically mutate that semaphore. If it manages to get that, then it can safely reboot. So for example, in this case, if we just had a three node cluster of servers, we would probably want to make sure, we would probably want to maintain at least 2 out of those 3 servers up and say they're all serving some identical web app. We want to make sure that at least 2 out of the 3 are available. So in this case, we would use a semaphore that just has a value of 1. And that's literally just stored in etcd as a document somewhere, a little bit of metadata, annotated metadata, and then a value saying, the value of the semaphore is currently 1. So server 3, which needs the reboot, it's going to talk to etcd and try to take a lock. This is sort of, we actually say lock here, this is sort of a library that we have, and essentially that just maps to doing a compare and swap in etcd on that semaphore key. The lock's successful, so it decrements the semaphore, so now the server can happily reboot. So now it's out of service, but we still have our other 2 servers. But while that server's rebooting, server 1 also applies the update, so now it needs to reboot. So it doesn't really know, it doesn't talk directly to server 3, never do any direct communication. Instead, all this is handled through etcd. So server 1 is just going to happily try and take a lock because it wants to reboot, but the lock's going to fail because when it tries to, well, the first thing it's going to do is it's going to see that semaphore value is 0. Or if they were both trying to, they both accessed at the same time and they both saw semaphore value as 1 at the same time, they both tried to use a mutation to decrement it, only one of them would succeed because etcd provides the guarantee of an atomic operation. So that failed. Server 3 happily comes back up successfully, and then the first thing it does when it's successfully booted is it does an unlock in etcd. When the semaphore goes back to 1, so now maybe server 1 is kind of asleep for a little bit. Later on it'll wake up and say, oh, now I can take a lock successfully, so then it can reboot. So that's kind of the classic canonical example of why we build something like etcd and what it's useful for. And it's quite a simple example, but it's very practical. Like this is the case for almost all CoreOS clusters. This is how they update. And then just yesterday I was talking to someone from who runs an Ubuntu cluster, and they also use locks. There's nothing particularly CoreOS about this, so they also use locks on etcd to coordinate their reboots when they apply updates every night, for example. Another good example of an application using etcd is SkyDNS. And SkyDNS is it's for sort of service discovery, and it's also a DNS server implementation. And it basically uses etcd to store all of its configuration. So SkyDNS exposes a DNS server protocol that all of that information is stored. VolcanD is another kind of interesting one. VolcanD is a programmatic extended policy. Simpler, think about it, some of the simple functions, it's a load balancer, load balancer that can be very fast, and also ready to go. And again, so it uses etcd to store all of its configuration, so that Vulkan processes can be sort of quite ephemeral, but have all of their configuration persisted safely. So load balancing across all these different actions, and it just reads and writes all its configuration into the etcd cluster. So then Vulkan can die at any time, and it can still maintain that persistent information. And then confd is another quite a popular project, etcd, that uses etcd, which is basically just a very simple template configuration engine. The way I sort of think about this is that it's sort of kind of dumb application. So in the sense that maybe in the future of this world of sort of decentralized microservices, everything would natively understand that it needs to load its configuration from something like etcd, some external service. That's highly available. But for now, a lot of things still rely on configuration files and don't have any other means of loading configuration. So something like confd is a great glue for that in that case. So confd will use that watch feature that I talk about to watch certain keys in etcd. And as you change your configuration there, confd will pull that down, create an actual high-graded configuration file of the application, and then can optionally reload your application. then finally, sort of tying a lot of these things together, you get something like Kubernetes, which is, hopefully most of you are probably aware of what Kubernetes is, but it's a sort of cluster orchestration system for running containerized applications in clusters, and it uses etcd pretty extensively as its data store. But again, coming back to the idea that etcd should be like that core component, but not necessarily, shouldn't be used for everything. So there's no like, you know, in Kubernetes cluster you have sort of some scheduler nodes and some API nodes, and then you have a whole bunch of worker nodes. And you don't have you know, all the worker nodes talking to etcd all the time or something like that. etcd is kind of behind the scenes providing this sort of safe configuration store. I want to talk a little about scaling etcd, some of the things that we've done in the last sort of 6 months, a year or so, and some of the things that products we've done. So, yeah, the version 2, the sort of version 2 branch of etcd, we've implemented a couple of things in the last, I guess in the last 6 months, like asynchronous snapshots and request pipelining, and then we have a bunch of cool stuff for coming in v3. So, asynchronous snapshotting. So the idea is that when you have this log-based system where everything is append only, excuse me, you know, since if you just have an append only log and you're always writing to it, then it can grow without bounds. So periodically you need to truncate the log, you need to be able to do a snapshot, and sort of so the snapshot of the state machine, so you don't need to contain the entire history of the log necessarily. So historically we did this synchronously in etcd, which means it was like a stop the world operation, and that was not uncommon in these kinds of systems at the time. But since with the advent of obviously this is pretty painful if you're trying to provide a consistent service or any kind of latency guarantees. So what we do instead is we now take a complete sort of a complete copy of the snapshot of the current log in memory, and then we can safely write that to disk, and then if any changes come in the meantime, we can mutate them in the original one. And just to give you an idea of like the kind of impact of that, this is a production etcd cluster that I think this is actually serving our discovery service. So we provide a service at discovery.etcd.io, which allows you to bootstrap your own etcd clusters, and that's actually backed by our production etcd cluster. And we just have this incredibly variable, this graph is just a number of 500s, I think, variable sort of performance when these snapshots were happening in the previous mode, and then as soon as we implemented asynchronous snapshotting, it essentially just completely went to 0. Another change we did is Raft, is moving to doing pipelining of Raft requests. So I mentioned Raft is like the consensus algorithm that etcd uses that all the nodes use to communicate amongst each other. And Raft fundamentally consists of certain RPCs that they'll use. Previously, we would sort of, every time we send an RPC, we send it and wait for a reply, and that's the next one, which is kind of naive. Now what we can do instead is sort of that, essentially just keep sending, optimistically keep sending RPCs, and then once we get we sort of assume that they're going to succeed until we receive the response, and then if we receive the response, then we can sort of recover from that. But then, really where we want to go with etcd is represented in v3. We want etcd to scale to thousands of nodes. So currently it's the v2. We sort of talk about it in the order of hundreds of nodes, but we really want v3 to be extremely in the order of thousands of nodes, and probably hundreds of thousands and millions of clients. So there's 3 sort of ways that we're achieving this with v3. The first is that there's a totally new API, and this is kind of a hard decision to make because no one likes breaking APIs, but ultimately there were just some things we wanted to be able to express that we just couldn't map into the existing API. So there's a few key changes here. The first is that rather than having this sort of hierarchical key space, so etcd exposes this like //bar, blah blah blah, and there's sort of implicit directories in that way. Now everything is just a completely flat binary key space, where you can have arbitrary binary keys and arbitrary binary values instead of this sort of directory-like hierarchy. And then one of the really powerful primitives is to have to do transactions. So that means you can actually mutate multiple keys at once, which is pretty powerful. And then these really common patterns like leasing and locking, we want to expose those so that people can use them without having to create their own recipes or things like that. We want to have really well-known recipes that people can use, just import them. And then finally, it's all based around gRPC, which is the new kind of RPC protocol. We think it's the future of RPC for things like this. So it's based around HTTP2 and protobuf v3. And there's pretty good, generally pretty good support for this in Go. So as I said, the key space is now completely flat, so you can just set any key you want to any value, and there's no like implicit directories or anything like that. If you still want to maintain sort of a directory-like hierarchy, then you just sort of layer it on top. But etcd itself doesn't need to be aware of that. The operations that excuse me, exposers, again, you sort of have your usual put and get, or set and get. And then we provide things like a range operation. So that allows you to get multiple values at once, multiple keys at once, and in a consistent way, so that you know you're getting them all at a certain snapshot. The only way to do this in previous versions of etcd was to do like a recursive get, but that can be very expensive. And you can also do this. You can also do a range operation against the range of keys. That's just kind of a basic idea of what they would look like. And then there's transactions. As I said, this allows you to do sort of multiple, potentially multiple operations at once. And so the idea is that you can always provide a precondition, and then when you start a transaction, and then you can provide success cases and failure cases. And this allows you to, in the precondition, you can check against multiple values at once. So as an example, you might want to check if a certain value is greater than another value, but you also might want to check, you can check multiple versions at once, and if they both succeed, then you can do relatively do the one operation atomically, otherwise it can do another different result. As I mentioned, watch has sort of changed a bit. So rather than in previous versions of etcd, we allowed you to watch from a certain point in history. So for example, if you wanted to watch all the changes to the key food, you could also watch from like 100 revisions in the past, or indexes in the past, to see all the changes that had happened. But again, since we have this compaction issue, we don't allow that to come down to the history. So etcd, the previous version of etcd, we just arbitrarily truncate in etcd v3, we want this to be controllable by the user. So you can potentially decide for certain keys you could retain the entire history, so you have an entire log of what happened to that key. But other ones you might want to keep a much shorter history. And then, as I said, this is all using gRPC, which has some really nice benefits over HTTP 1.1. Particularly in terms of sharing a TCP connection. So now, previously, like if you had etcd clients that wanted to watch multiple keys or something like that, they'd actually initiate multiple connections. But now we can actually share them over a single connection, so that etcd client can have a single connection to the etcd server up to that connection. Also, this is part of our coding, which is arguably more efficient than JSON and you get all these, since we define the etcd API in gRPC, or in protocols in gRPC, you can kind of automatically get all these nice libraries generated in all the languages that gRPC supports. So another change in v3 is that, so I mentioned that we did a snapshot, and I mentioned that we now sort of do that asynchronously, which is nice, but then the next sort of step is that we want to be able to do it incrementally. So instead of having to snapshot the entire state every time, we can just say the delta from the last time that we took the snapshot. And again, that just sort of lowers the I/O and the CPU necessary, and you get much more stable performance. And then the sort of other interesting change in V3 is that we're moving to using a disk backend. So instead of necessarily keeping all the values in memory, you can keep your entire etcd stored on disk. And then we actually, in the current implementation, we basically just use a library called VoltDB, which is a pure Go LNDB based, similar to LNDB database. And the idea is that it keeps all the data on disk and then maps it into memory, and then we basically use the kernel's caching to make sure that all the hot data stays in memory, so it's still very quick to access it. The interesting thing here is that now you're only bounded by how much disk you have in terms of how much history you want to keep. So as I said, potentially you can keep the history of the entire history of a particular key or something like that. And then we expose this to the user in terms of when they want to compact the history and get rid of old versions of the key. So this means that etcd basically becomes an MVCC, like a multi-version system. So, over time, for a particular key, we might have very first revision of that key. And the next time we do a put to that key with a new value, we basically just increase the revisions. And then, if I just do a simple get, then I'll always get the latest revision for that key. But if I do I can also do a get on a particular revision to get the result from that. But as I said, we want this to be controlled by, you can't always keep everything in history, or you can't always keep everything on disk, because you'll just end up using infinite disk. So we expose something called compaction to allow you to get rid of all the revisions that you don't want. So the way that this works is that if you sort of mark these old revisions with tombstones, or that's what etcd marks it with tombstones internally, and then any key that has a tombstone applied can be removed, and then you always keep the latest version of the non-tombstone one. And then after that's being triggered by the user, we do that. We can which ones are going to be removed, and we do that completely asynchronously in the background to not block any other operations to etcd. And then, yeah, you can also get sort of while a snapshot is happening and do sort of a range across different versions. Okay, so I mentioned that we also want to expose these really important derivatives for building distributed systems. We want to expose them more natively. So we want that to make it as simple as like in Go. It's just like importing a release package, for example, and then being able to just create a list. So a release is a way to attach like a particular session to, so for example, a client can claim ownership of certain keys and things in etcd. So in this case, we create a release that's going to last for 10 seconds. And then when we do an operation in etcd, it's associated with that particular release. And then while this is a way of doing things like attaching sort of ownership to a key, so that for example, if you were going to simulate who a leader is in a cluster, that it could be the current owner of a particular key explored in etcd. As I said, we also have this watching primitive. So this looks pretty simple, ends up looking pretty simple when you expose it in the Go library. So for example, you just set up a new watcher on a particular key, and then that just returns code is a little bit wrong here, but it returns a channel that you can simply listen on to get all the events that return. And then we want to provide these slightly higher level things like leader election and locking we want to expose that natively at least in sort of Go and ideally in the API itself. So we have packages for all these things now that you can just import and use directly in the application without needing to worry about mutating any keys yourself. So for example, I talked about like leader election. It's a way to safely guarantee that you have at most one sort of among your cluster, you have one owner of a particular key at a time. So then that person can be that node can be the leader and do all the mutating operations, safely knowing that no other nodes are able to gain that leadership. Similarly, you have sort of locking, which is able to kind of similar principle about able to sort of take ownership of a particular resource for a particular period of time. And then barrier is sort of the inverse of that. So it's an in Go. As I said, we use Go for everything. We really like it, but basically for the same reason that everyone likes Go. It's super easy, super really fast for us to develop and to iterate. Because we're making doing a lot of these changes sets in Gig. And by and large, we really like the standard libraries. We just try to leverage them wherever possible. But also, there's such an active ecosystem that we can all these cool, we can leverage all these other cool libraries like something like FOSDEM, so we don't need to create our own storage, entirely new storage backend. We can use something that's already out there and already pretty well tested. And then, yeah, obviously the concurrency we use pretty extensively to be able to serve multiple clients at once, to do things like consensus algorithms, to do that in its own dedicated code routine. And unfortunately, I'm kind of out of time, and this slide's a little bit rushed, but I did want to, this is kind of like exercise for the reader if you're interested in looking into some of the kind of fun issues that we've had with Go. There was a sort of blog post that went out a few months ago around this thing about etcd linking file descriptors, which turned out to be a sort of interesting thing in the Go HTTP library, where when you mixing these two, not two, arguably somewhat niche Go HTTP 1.1 features of pipelining and close notify, that you can end up sort of missing implications. And sorry, totally out of time, but happy to talk more if anyone would like to.